Hi, Dr. Pitcher here, and in this video we're going to take a look at the preparation of alcohols. Now, we have seen some ways to prepare alcohols so far, and alcohols actually play kind of a central role in the, in organic chemistry. You can look at figure 17.4, which I'll recreate for you here. We have alcohols in the middle. Now we've already seen ways to turn alcohols into alkenes. So C double bond C, and we'll call alcohol here ROH. And we've actually seen some ways to convert alcohols into alkyl halides and alkyl halides into alcohols. That was chapter 10. We can convert alcohols into ethers, and on the chapter 11 quiz there was actually a question where you were making an ether. Now, we will see, that didn't come out straight, but oh well. We will see ways to convert alcohols into aldehydes and ketones, and also ways to convert aldehydes and ketones into alcohols. Another couple of functional groups that we will look at converting alcohols into, and converting them into alcohols are carboxylic acids and esters. So just to circle ones that we've seen that. I should add in here ethers. And we've seen how to convert alcohols into alkyl halides. Okay. I can show you a few, just to review a few of those reactions here. And what we've actually seen is we can convert an alcohol into an ether, although we haven't seen how to convert an ether into an alcohol. I'm not sure if I'll talk about that. Anyway. So there are some ways of preparing alcohols that we have seen. So let's say we had the following. We can do a simple hydration. We could do HgOAc2, H2O, and NaBH4, hydroboration oxidation. We could do BH3.THF, followed by H2O2 and OH minus, and that gives us our anti-Markovnikov product. And again, that's going to be syn. Let's see, what else can we do? We can go ahead and do a syn hydroxylation, so OSO4 H2O2, or KMNO4, cold and dilute. And we could do MCPBA followed by H3O plus or OH minus. We'll just do H3O plus, and that will give us now our anti-diol instead of the syn diol. So these are all ways that we've seen so far. Now we do have some other ways to make alcohols, and I'll talk about those. And one way that we can make alcohols is by reducing carbonyls. First, we need to have a definition of organic oxidation and reduction. And it is something that I did talk about in class on Friday, but I figured I'd record it again. And we can abbreviate oxidation reduction as redox, reduction oxidation. Now you may remember oxidation as a loss of electrons and reduction as a gain of electrons. But typically what we'll look at here is hydrogen and oxygen. And so an organic oxidation will have a net gain of oxygen and a net loss of H2. And organic reduction will be the opposite, a net loss of oxygen or a net gain of H2. So, for example, actually, if we had if we did our epoxidation, that is an oxidation. Okay, I've gone from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C6H10 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C6H10O. I've added an oxygen. An example of, reduction would be something like H2 and platinum, where now I've added, so right here, gained oxygen, gained H2. Something like hydration are going to be neither oxidation nor reduction. Okay, because hydration is adding H2O. So we're adding H2, but we're also adding O. So for example, I could have that molecule before, and I could do HGOAC2, H2O, followed by NABH4. Now, what have I done? I've gone from C6H10 to C6, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C6H12O. So I've added H2O. So those offset. Technically speaking, I've oxidized this carbon because I've added a carbon-oxygen bond to it, but I've reduced this carbon because I've added a carbon-hydrogen bond to it. So this is just something to look out for. And on the exam, you will have to identify reactions as oxidation or reduction or neither and provide a brief explanation. And you can just use these definitions as your explanation. So let's look at reducing some carbonyls. Okay. Excuse me. Typically what we'll want to do here, and sorry, I feel like don't have things centered here. I just want to make sure you guys got this, so feel free to pause and copy that down. Okay. We can take a ketone and use something like LiAlH4, or we could actually use NaBH4. So we'll say or NaBH4, and then water or H3O plus, and we'll get RCHOHR prime. This works for aldehydes as well. LiAlH4 or NaBH4 plus RCHOHH. And reducing a ketone will give us a secondary alcohol, and reducing an aldehyde will give us a primary alcohol. So we're not going to be able to make a tertiary alcohol in this manner. There are other things that we would have to do. Now, what is LiAlH4 and what are NaBH4? Well, these are reducing agents. In particular, they are hydride or H- sources. Now, what would this look like? So, you know, if we're going to draw a mechanism of these reactions, what would it look like? Well, AlH4 minus Li plus and then we can have the borohydride minus Na plus. And these function as hydride sources, so we'll get a hydrogen and its pair of electrons. Now, one thing to note is that LiAlH4 is more reactive. We use NABH4 in 12B, and it's pretty innocuous stuff, all things considered. Lithium aluminum hydride you definitely want to use in the hood. It's kept very dry. It tends to react violently with water. We also refer to LiAlH4 as LAH, so you may see that, LAH, as an abbreviation. And just to show the mechanism here, give you guys an idea, we'll have our AlH, H minus charge, and we'll have our RC double bond O R prime. What happens is the H minus goes to form a new hydrogen-carbon bond, and then we'll get our, this really isn't reversible, so I'm just going to write that arrow like so. Now we get O minus, we have an H there. And then we'll add H3O plus. So again, this isn't present when you start out, but you have to add it later, and we will get our product. Okay, so we have a nucleophilic addition of the hydride, the H minus, which is a good nucleophile. It's a good base as well. And we do that, that adds to the carbonyl to make this alkoxide species, which we then protonate to get the final alcohol. So you wouldn't necessarily want to do this if you had, with lithium aluminum hydride, you wouldn't necessarily want to use an alcohol as a solvent, because that could produce, you know, this guy H minus could just deprotonate the alcohol. NABH4, you can actually do that in ethanol because the hydrides from the BH are not as reactive as the hydrides from the ALH. Anyway, so now we've seen ways to make both ketones and aldehydes from to make alcohols from ketones and aldehydes. I'll get to ways of making aldehydes and ketones from alcohols in just a little bit. Okay. One thing to note is that C-C double bonds are not reduced by LAH or NABH4. So let me just kind of write that off here to the side. So if we had something like this, and we did 1LAH, 2H3O plus, we would get OH. Now, if we wanted to reduce this, we could go ahead and use we could go ahead and use H2 and palladium. The only thing we have to worry about is H2 and palladium. If you have a real excess, you'll end up reducing the CO double bond as well. Some texts say that that happens readily, some say not as readily, so it's best just to avoid using there are ways that we can actually protect this guy, and so if we did reduce everything by adding H2 to both, we could get back the ketone. But we'll talk more about that later, actually probably next semester. But just remember, CC double bonds are not reduced by these hydride containing agents, lithium aluminum hydride or sodium borohydride. Okay, now we can also reduce esters and carboxylic acids. So we could do RCOH, RCOR prime, and then either of these will go ahead and use our Li, so use our LAH and H3O plus. They tend not to react as readily with sodium borohydride, so we'll talk more about that. Oops, that's a 2 there, 2H3O plus. We'll get RCH2OH, and here we'll get RCH2OH plus R prime OH. We'll talk more about the reactions of these guys next semester in 12B. All right. Now, one thing that's actually missing from here, from this one, is we can make alcohols from nucleophilic addition to carbonyls. And that is our Grignard reaction. So I've talked about the Grignard reaction in what was it? In the synthesis lecture, sorry. But I'll go over it again here. So if we have some kind of halide and treat it with magnesium in ether, we'll get RMgX. Magnesium inserts in between the halogen and the alkyl chain. And this is a Grignard reagent. We can then add an aldehyde or ketone. So let's say we do RCR prime, double bond O, in ether, and then quench with acid, and we will now get, let's make that double prime. We will get R double prime C R prime R O H. And the way this works is as follows. We'll have RMgX. So for our mechanism here, start with RMgX, and then we'll have R double prime C double bond O, R prime, lone pair. We'll get a nucleophilic attack by the electrons between the in the carbon-magnesium bond here, and then that'll kick up. So it's kind of like the hydride attack. So it's a nucleophilic attack on that carbonyl carbon. And that's going to give us now R double prime C R prime O minus, and then R there. And actually this O minus is going to be, the counter ion is going to be MgX plus. Mg is a 2 plus, so MgX would have plus. And then when we add our H3O plus, we'll go ahead and protonate, giving us R double prime C R prime R O H. So a relatively straightforward mechanism. Now there are some things to note here about the Grignard. So we can make Grignards from alkenes and benzenes. So we could have MgX, and we can have MgX, typically MgBr. Okay. Now, what is it going to look like when we do our different Grignard reactions? Because we don't have to use a ketone. We can use an aldehyde, and we'll get something else. So let me just show you the different variations here. Okay, so we've seen ketone. So we'll have our ketone, and we'll do 1R-MgX 2H3O plus, and get our product will be a secondary alcohol. Sorry, tertiary alcohol. If we use an aldehyde, or MgX 2H3O plus, we will end up getting a secondary alcohol. And if we use formaldehyde, or MgX followed by H3O plus, we will get a primary alcohol. We can also use carbon dioxide. So if we took CO2 and treated it with a Grignard, what you'd actually do is you'd make your Grignard and then bubble CO2 through it. There's a version of the Grignard lab that does that. I'd like to try that sometime. We're going to now get RC double bond OH, a carboxylic acid. Now we can use a carboxylic acid So let's try acetic acid here. And treat that with RMgX followed by H3O plus. Now the first thing that's going to happen is actually the R minus here is going to deprotonate, and so we get a we'll end up getting this O minus MgBr, or MgX I should say, plus RH. So we're not going to do it this way. Instead, what we'll do is we'll use another reagent, and the text mentions this. It's called a turbo-Hauser base, which is a isopropyl. Let me see if I can write this out here. So we've got R2 MgCl IPR2 N MgCl.LiCl, whew, followed by erg. Sorry, I did that in the wrong order. Whoops. Let's do it this way. Let's just do it this way. Boom, boom, OH. Let's do this up here. Sorry about that. We'll do one. We'll use T, BU, MgCl, and 2. We will use the turbo-Hauser base, which is R2 MgCl plus the IPR2, so 2 isopropyl groups attached to a nitrogen attached to MgCl, complex with lithium chloride. Kind of a pain to remember. So this is our turbo-Hauser base. And we will end up getting now a ketone. I don't know if I would necessarily try doing that. And then the last thing that we can do is we can use an ester. I apologize for squeezing this in at the bottom here. I had to scribble that out. So we could have, let's say, methyl acetate. Let's just do ethyl acetate. And then we'll react this with 2 RMgX. Sorry. 1 is 2 RMgX, 2 is H3O plus. So one of these will actually add in, and then we need another one to add in and kick off this, the O CH2 CH3 group in this case, and we will get now R OH plus boom boom OH. And so what we end up getting now is a tertiary alcohol, which is that guy there. And we also get, as a side product, another alcohol. Mostly we'll focus on these guys up here. Okay, these are kind of the big ones that we really want to think about. Reacting with a ketone, aldehyde, formaldehyde, or carbon dioxide. I should actually put that aside. Since we're not talking about making carboxylic acids yet, I just wanted to mention you can do this. So let's cover that up. And so we'll focus on these guys and maybe the ester one. Okay, but for synthesis, these will be the most useful. All right, so let's see here. have I talked about all the ways that you can prepare an alcohol? I think I have. So if we go back to our table here, we can see that we've looked at using ketones to make alcohols, using aldehydes to make alcohols, the Grignard reaction, and then esters, using those to make alcohols. Carboxylic acids to get alcohols is a little bit different. We actually, well, we did see, hold on here, we can reduce those. If I can find my reduction. Yeah, we saw the reduction, but we can't use the Grignard to make an alcohol that way. All right, so in the next lecture video, we'll go ahead and take a look at some of the other ways here. So making a ketone or an aldehyde from an alcohol, or making a carboxylic acid from an alcohol, or making an ester from an alcohol. So, and we'll actually talk about making ethers from alcohols and a little bit more, I think. I'll try to talk a little bit about using some of these reactions in synthesis as well, but we'll probably get to that a little later in the week. All right, so hopefully that was a good overview of all the reactions that will make alcohols for us, some that we've seen and then some new ones. And we'll talk about reactions that alcohols will undergo in the next video. All right, until then, stay safe out there. Bye now.